Hello, in this screencast, we're going to walk through the process of completing number 11.12 on page 218 from our text. Um, this problem starts off a little vague, so you have to read and think a little bit about what's going on. It discusses a production line at a candy plant designed to yield 2-pound boxes of candy who the actual weight is normally distributed with a mean of 33 ounces and a standard deviation of 0.30 ounces. So basically, what's happening is in this, they're doing a little quality control. If the assembly line is supposed to have a mean of 33 with a standard deviation of 0.30, they're going to randomly select, in reality, samples from that production line to make sure that the production line is actually doing what it's supposed to be doing. And in this case here, they randomly selected 36 boxes from the production line. And of those 36, that yielded a mean or a sample mean of 33.09 ounces. So this is the key information right here that is given from the actual text, the scenario. And then the first question is, describe the population being tested. Well, on a production line in a factory, the population being tested is actually um, all of the boxes of candy from this single production line ever created, in the past and ever created in the future. So it's obviously a population that you can't sample all of them. So efficiently, what they would do is periodically random sample selections of them to make sure, again, that the line is actually producing what it is designed to do. So the population is all boxes produced by this assembly line. So that's for part A. Part B says, using the customary procedure, test the null hypothesis at the 0.05 level of significance. So the first key step with this is identifying what type of hypothesis or alternative hypothesis we're going to create. So this is going to be a two-tailed test. So if you think about it, if we're hoping that this is designed to produce boxes of 33 ounces, quality control has to make sure that the the machinery is not producing either too high or too much weighted boxes or too low. So it has to test for both. So in a two-tailed test, what we're doing here is then we have a normal curve, and again we're hoping that on average the mean of all the samples is 33. But if we produce a sample that ends up in either a higher end or a lower end, either one of these two tails, then what we're going to do is make a determination that there's a problem with the production possibly, and something has to be fixed. So the first step is, again, identifying what type of tail, whether it's a one-tail or two-tailed test. In this case, it's a two-tailed test. Customarily, if the research question or whatever the scenario of the problem is, if it does not give you a very specific, either greater than or less than indication, or if the research is looking for an improvement or a significant decrease in something, those are the cases where it would be a one-tailed test. But if it doesn't come out and actually say either direction, then we need to account for both. So in this case, it's a two-tailed test. Our null hypothesis is going to be that the mean is 33. So population mean is equal to 33. And our alternative hypothesis states that the population mean is not equal to 33. This is what we're going to use here to indicate for allocating for either greater than and less than. And then the level of significance, or alpha, is going to be 0.05. Now recall from previous problems as well, if we're taking 0.05 and splitting up into the two tails, then what we're doing is we're centering 95% of the probability here with a tail of 0.025 here and 0.025 there. That yields, if you recall, a critical value of positive 1.96 and negative 1.96. How that is found, just to remind you, is from the back of the book in the table. If you look for what type of z-score yields an area of 0.025 from that point towards the tail, then we end up with 1.96. So we need to be prepared for either a critical value, or this is again our make or break point. This is our boundary of positive 1.96 or negative 1.96. Carrying through the hypothesis test, then we take a look at, we need to find the z-score for this sample. So the z-score for the sample is the sample mean minus the population mean. That gives us our difference. The textbook calls that the effect size. And then we're going to divide that by the standard error. Again, we do not just take the 0.3 and plug it in here as the standard deviation. It's the standard error. Because what we're doing is now not finding a z-score of a single point. We're finding a z-score for a sample. So the standard error, again, is the standard deviation of the population divided by the square root of the sample size. So we have all four terms right here that we need, and we're going to plug them into this formula. Personally, I take my time. I take care of the numerator first. I take care of the denominator second, and then I divide. And based, again, on our mean of the sample of 36 selected items that yielded a 33.09, it yields a positive 1.80 z-score. That falls in the interior of the curve here from our make or break point of 1.96. So since it falls in the interior here, then we are going to retain our null hypothesis. The difference was there. It was 0.09 ounces greater than it should be, but it is not a statistically significant difference and not different enough for us to consider that there's an issue with the actual mechanism producing these, and we retain the null hypothesis. So if you're in quality control, you're in good shape. We don't have to do anything to it. So that's a walkthrough for part B. And then part C asks the question, or poses the point, someone uses a one-tailed upper tail critical because the sample mean of 33.09 exceeds the hypothesized population mean of 33. And the book asks any comment. So there's two issues with this. First issue is the fact that it is a one-tailed test. If we're dealing with quality control from this system, we want to again allocate from the directions, or the fact that the directions does not tell you one direction or the other, then we need to make sure that we conduct a two-tailed test. All right, that's the first part. So the one-tailed test is a mistake, and a two-tailed test would be the appropriate, unless, of course, the original prompt tells you that we're looking to either exceed or decrease significantly in one way or the other. The other part fundamentally is this. It is inappropriate to determine what type of test to run after you've selected your sample and calculated it. All of this procedure right here of establishing what our hypothesis statements are and what our level of significance is, all actually should be done and taken care of prior to us taking a sample. Otherwise, if you think about it, human bias is going to enter, and if you start taking a sample and you're conducting high-level research one way or another, that's inappropriate. So the bias is played into too much, and it is inappropriate to determine what type of test you run after you select the actual sample. Hope that helps for 11.12 and makes a little more sense of hypothesis testing. Thank you.